We, the coordinators of IISER Pune's Maths Club, are honored to introduce you to Dr. Sudeshna Sinha from IISER Mohali, who will discuss the captivating field of study that is chaos theory. Dr. Sinha is one of the world's most sought after specialists in the field of nonlinear dynamics and chaos theory, among others. After completing her PhD from TIFR Bombay, she went on to work at several institutes of eminence, such as the International Center for Theoretical Physics and the Institute of Mathematical Sciences. Over the course of her illustrious career, she has won several coveted awards such as the J.C. Bose National Fellowship as well as the B.N. Birla Prize. Her work currently focuses on the uses of chaos theory in computation, complex networks, and nonlinear dynamics. The Watersex talks aim to expose the undergraduate students to areas of research in mathematics which they may not learn much about during their first few years at college. Without any further ado, let's begin.
Right. So thanks for that. And let's see how far we can go. So what I was planning was a kind of a crash introduction to key concepts. Let me share my screen. You do see it, right? I hope.
Yes, ma'am.
Yeah, okay, great. Right. So what I was sort of planning to do was, you see me too, I hope, right? I mean, it's a bit, can you see me in the corner, or you just see my slides? I can't tell.
Yes, ma'am. Your video as well as slides are visible.
Okay, good. Okay, so we are set. Right. So, so what I thought I'd do is, I'm trying to condense like half a semester's lectures into an hour. So I have to give up something. So what I thought I'll give up is details. Okay. And I'll give up some details in favor of, a broader picture so that, you could, of course, later on you could fill in the gaps if you feel interested enough. And of course you can always ask me for more papers or references after the talk, or even by email. So I thought I'd start with let me see. Yeah. So let me say a few general words first, okay, before getting into the meat of the talk. So what we are looking at is classical phenomena, okay, classical mechanics. And the thing is, I always like to misquote the famous quote by Eugene Wigner. So what always feels remarkable is that it is so unreasonably effective. I mean, it has almost no business being this good, okay? And the mathematicians like it because it's rigorous. The physicist, well, it describes phenomena from nanomechanical oscillators to astronomical objects. So it literally scans like orders of magnitudes in spatial scales and temporal scales. So it is their workhorse. And interestingly, it is the workhorse of engineering sciences as well. So when I was an undergraduate in IIT, the only physics we learned was classical mechanics, literally the only one. And that was because that's all they really needed. So it drives to date a whole lot of physics. Now, what is chaos? You can think of it as a new frontier in classical mechanics. Okay, so when you say classical, it's a kind of polite word to say really old. So classical mechanics is 300 years old, but this is like a new kid in a very old block, and it has caused at least engineering and physics people to reassess the way in which to view the classical physical world. Okay, and to see where it comes from. Well, in some sense, the eternal quest is to foresee the future. I mean, that's how these astrologers make so much money. So one of the beautiful things about classical physics is that it is deterministic. Okay, so if you know the properties of the system, so you can, system could be just a single particle, it could be weather patterns, which involves like millions of particles. But if you know the system and if you know the laws of physics, then the idea is that you can perfectly predict the future. So this is what underlies the idea of a clockwork universe and predictability in general. But so classical mechanics seems to be chugging along. So why would you even need a new idea? So the surprise was this: a large range of seemingly simple natural processes. So you don't even have to put in all kinds of complications, really simple systems seem to exhibit enormously complex behavior. Things you can't just describe by elementary functions, like sines, causes, exponentials. It's like really, and some of it even looks to the eye aperiodic. So it appeared as if these simple deterministic systems were driven by random forces, though they weren't. And they were, in effect, essentially unpredictable. That this made everyone sit back and reassess the way they thought of the classical world. And this new paradigm shift is the new theory of chaos. Okay, it's often called a new science. So the first hints that nature can be both deterministic and unpredictable. So you wouldn't have thought you'd use these two words, which are, delicious contradictions in the same sentence. But the first hints that actually this is true, it goes back to 1800s actually. So the king of Sweden had offered a prize to anyone who could solve the so-called three-body problem. The two-body problem, everyone can solve. It comes in your physics 101 or whatever elementary, or at least the starting physics courses. All of you know how to do it. But the three-body problem, so you throw in one more body and all bets are off. And you don't know what is going on there. And the French mathematician Poincaré actually won the prize, like a true mathematician, without actually solving the problem. So instead of solving it, he wrote down very clearly, of course, being a good mathematician, all the reasons why it couldn't be solved. Okay, it's very important to know that. And one of the important reasons he highlighted was how small differences in the beginning of the system could lead to enormous differences at the end. Okay, and so to paraphrase it a bit more colloquially, the present determines the future. That is determinism. But the approximate present does not even approximately determine the future. Okay, so that is the problem. And the other thing which came much later, 1962-ish, was from an atmospheric scientist. Okay, and he was actually doing something which was not mathematics. He was simulating a bunch of equations on one of the early computers. And so he was studying a simple model of the Earth's weather. As it happened, three coupled ordinary differential equations. He somehow made a toy model and had this, and he was trying to figure out the solutions because it was not analytically tractable. So he stopped and started his simulation and ended up with wildly different results. So he serendipitously and without actually looking for it, he stumbled across chaos. So this was this extremely surprising sensitivity he found to initial conditions. So going for lunch in the middle of your simulation was not a good idea for him. So the tiny rounding error that he had, 1 part in a million, that was enough to give extremely different behavior very, very within a few time steps. So the broad umbrella, so now to come to the nitty-gritties. So the broad umbrella of this, field, it would be called dynamical systems. That would be a broader term for it. So let me sort of put what I exactly mean by the word. So this would be a mathematical prescription for evolving the state of a system forward in time. Okay? That's it. So if you thought of your time as a continuous variable, you have a flow, and typically, one of the best descriptions of it are ordinary differential equations or differential equations. And that is how most of you would have encountered a dynamical system, like Newton's laws, for instance. But what I will do for the rest of it is the other class, another class of dynamical systems, where it is easier to understand difficult concepts early on, which would be maps. So these are functions, iterated functions, which describe the evolution of a system in discrete time. So n is an integer, so it's just ticking like clockwork at the background. And x is the state, which is updated according to this function f. So x is a point. It could have many, many components in n-dimensional phase space. And this map just gives you the next point at the next instant in time. Okay, and this orbit or this trajectory or this flow, I shall use all these words interchangeably, is what you're trying to get a handle on. Now, so in all of this, if I say n is the dimension of the dynamical system, or some people would call it degrees of freedom, how large does n have to be in order for chaos to be possible? Okay, so if the answer was, Avogadro number or something, then, you're not so surprised. You have an enormously large complex system, so something complex comes out of it. Yeah, okay, you're not that impressed, maybe. But the answer now would be that extremely small systems are also capable of showing chaos. So I will state this without proof, that for systems whose dynamics are described by n first-order autonomous differential equations, the smallest system capable of displaying chaos is 3. So essentially, a system of ODEs with 3 equations is enough. That's just the necessary condition. Okay, so here is a picture, okay, of a double pendulum. So a single pendulum doesn't cut it. Why? Because single pendulum has one angle and one partner momentum, angular momentum. So it has 2 variables. So 2 variables is not enough. Okay, it has to be greater than or equal to 3. However, throw in one more angle. So you have a pendulum, one bob, put in another bob. So here is one bob, one single pendulum, but you've thrown in a second bob. So there are 2 angles you have to keep track of and 2 partner momentum. So your phase space now is 4-dimensional. 4 is greater than 3. And indeed, it gives this extremely complicated orbit, which I have drawn. This is a physical pendulum tracked by an LED, just to give you a sense of what it looks like. Okay. Now for maps, which is what we are going to do today, is if you had x, which is x1, x2, all the way to xn, if the map is invertible, that is to say, if the inverse of f exists and is unique, so it has one unique pre-image, then you can get chaos for n as small as 2. So you just need two coupled equations here. So say, for instance, xn plus 1 is some function of x and yn, and yn plus 1 is some other function of x and y, and that would be enough. But what is even more simple is a non-invertible map. So if the map is non-invertible, if its inverse does not exist or is not unique, then you can get chaos for anything 1 onwards. So then the necessary condition is just 1. So a 1-dimensional non-invertible map is essentially the simplest system capable of giving chaotic motion. So it's a very convenient starting point, because in your head, you can almost do the iteration. And what is nice is it's a great investment in understanding, because a surprisingly large proportion of phenomena that you get in higher dimensional systems is actually present in the 1D map. It's amazing how much there is. Okay. And to think that you can get something so random, so complex looking from something which looks absurdly simple is, of course, the big surprise. So we will do this in the next 45 minutes or so. So let me start with the simplest 1-dimensional map, which is not linear. Okay. So the simplest not linear map would be a piecewise linear map. Okay. So this would also tell you that there is an importance of not being linear or being non-linear. So look at this map. It is called a tent map because of its shape, kind of like a tent. It has 2 linear paths. So it's piecewise linear. There is one with slope 2 and the other with slope -2. And if you plot this function, you will get something like this. Of course, this one runs down outside the interval, like 2 straight lines all the way. Now, the interesting thing here is, if I take initial condition, which is negative, at the next point, it will become doubly negative, and in no time, it'll just hurtle off to -infinity. So it's going to double its distance from the origin in the negative side. There's no pulling it back. So it just goes off to -infinity. On the other end, why? Because this one becomes more and more negative. So any initial condition I start here at xn plus 1, it's going to get more and more negative. If I start beyond the interval at 1, so say 1 point something, at the next iterate, so the next iterate is negative, so it goes here and then also rushes off to -infinity. However, in the interval 0 to 1, the map, which is this, is bounded between 0 and 1. So all orbits are bounded in the interval. So at least you don't have to worry about things moving off to infinity. So if I have a map of the interval, it is onto itself, and there is no problem. You can track the orbit and get a sensible answer for it. Here is a picture. You can produce it with a short bit of code, 5 lines, with your Python or whatever. It's actually, this is a field where it's wonderful to write short code and get lots of pretty pictures, which illustrate the point. So here is what the iterates look like. So this is the iterate number n, okay, 1, 2, 3, all the way to 100. And this is x at n. So I start off somewhere. I don't know, I think I've started at 0.45 or something. Doesn't matter, I start somewhere. And I just push it forward. I push it through the function and spit out the next xn, and I keep going. So it's an iterated function. And it's a dynamical system because n is a counter for time. So as the counter ticks, your state changes. And if you look at it, the first feeling is, if you didn't know, it came from this exceedingly simple function, which is 2 straight lines. That's it. And it gave an output which looks like so. So the first surprise, without doing anything more, is that here is a system so simple. And if you look at the xn, and if I gave you a random number generator, say from your machine, I say I pick up a uniform random number generator and just keep pushing it at every iterate, I can guarantee you wouldn't know the difference. Okay, so it's that complicated. Now, what is the basic action of this map? There are 2 actions. One is stretching and the other is folding. Now, the stretching part leads to the exponential divergence of nearby trajectories by a factor of 2 at each iterate. So if you take x and x plus delta, it is, of course, going to go to delta, etc., etc. But we also need the folding. The folding is what keeps it bounded. So you push. So basically, you have to cut it and paste it back into the interval. And that keeps it bounded. And it also makes it non-invertible. Okay, why is it non-invertible? Because there are 2 different values of xn which map to the same xn plus 1. So 2 pre-images, not a unique pre-image. Okay, that is why you call it a non-invertible map. And here is a picture of a 2-dimensional map. Rather similar, just to show that this stretching and folding action is actually common even in higher dimensions. So this map is called the cat map, or sometimes called Arnold's cat map, after mathematician Arnold. And it's again very simple. Here is the map. Xn plus 1 is 2xn plus yn. Yeah, did someone say anything? No, okay. Okay, I didn't. So, and yn plus 1 is xn plus yn, okay, mod 1. So I keep the remainder folded back into the box. So the first action is to stretch. And the second action is to fold back into the box. Okay, oops, sorry. And what it does in just one iterate is to mangle this poor cat's image into something completely unrecognizable. One iterate of this very simple mapping. So what have I done? I've taken every pixel from this pretty picture of a very innocent looking cat, just to show you it's not just quantum mechanics which has cats, but also classical mechanics. So here is the cat. And here, in one step of this map, this is what it looks like. Literally torn, stretched and torn and fed back into the box. Okay. So this stretching and folding is very, very common and actually underlies a whole lot of chaotic transformations. Okay. Now, to demonstrate that this, can we sort of demonstrate that there is enormous sensitive dependence of initial conditions? To do that, what I'll do is I'll compose this map m times. Okay. So basically, I take f, then I do f of x, f of x, in order to get the mth iterate. Okay. So basically, x, if I start at xn, to go at xn plus m, the mth iterate, starting from xm, I will have to compose the map m times to f of x. So the first iterate is f1, which I just called f. So I have xn, then I get f of xn, which gives me the iterate. Okay. Now, this is what the tent map's second iterate looks like. It looks like two tents. You can do this through any graphics program, or just by thinking it through as to where the zeros and ones are mapped, and it's linear in between, so you can easily see it's going to be two tens. Second iterate, this one. Okay. Now, this is the sixth iterate. And oops, it has an extremely large number of tens. Okay, so it has split into this really, this completely, very large number of 10 by the sixth iterate. Okay, so it looks like rather that something quite interesting has happened. But what can we deduce from it? So what we can deduce is something interesting. If you have an initial condition which lies between 1 by 2 to the power m of some point, say xm, it can lie anywhere in the interval 0 to 1. Let me see that. So basically, suppose I am here. I made a tiny mistake in my initial conditions, okay? Or I don't know it, my machine doesn't keep so many decimal places, or my apparatus does not measure beyond a certain accuracy. So I have some uncertainty. And if my uncertainty is this small, my error in the mth, that is the sixth iterate, can be anything between 0 and 1. Okay, because you see, if I made this small an error, my answer could be anything from 0 to 1, which is the entire interval. So essentially, my mistake at the sixth iterate is as much as you can possibly ever make. So in short, it's not predictable at all, because you could not get the answer at all. Your error was as large as the interval itself. So absolutely no knowledge of the location of future points after this m. In this case, I'd done it for 6, even though your initial point was within reasonable precision. It's not bad precision, okay? So this is why it is called this is the root of this extreme sensitivity of chaotic orbits to small changes, okay? So even though, so basically what I'm telling you is that you have in your system some, you have a lovely laptop with, say, 64-bit precision, which means till 64 bits, you can hold your laptop company to ransom, to say, you give it to me. But the 65th bit could be just 0 or could be 1 or whatever, is the hardware. And which means that after that point, you have no idea what your system is going to do after that many iterates, okay? So which is the real problem of this, that it's deterministic, it's simple, but it's effectively unpredictable. Now I'll do it another way. Here is another map, piecewise linear, okay? So these are these two pieces, okay? These are the two lines. So last time it was a tent, so now there are these two maps. You can also think of this actually as a map on a circle if you want. Okay, so this has a stretch, a twist, and a fold. Okay, that is the action of it. This is often called the bit map or the shift map, I think mostly, or just 2x mod 1 map. Okay, which is the thing. Okay, so I have just done 2x mod 1, and I have plotted this f of x on this graph. Now, the interesting thing about this map, which makes us do a lot of calculations easily, is that you can think of this as a Bernoulli shift, which is to say that the action of the map, the iterates, is just a shift of the binary decimal point. So suppose I start with x naught. I express my initial condition as a binary decimal, okay? So here, this is A1, A2, A3. Each of these could be 0 or 1. I've expressed it as a binary decimal, which is, of course, what most of your computing machines store things as binaries anyway. But here it is nice because of this 2x mod 1, this thing is essentially, the dynamics is essentially that the decimal point just keeps shifting down the place. So the next iterate, starting from x naught, which was a1, a2, a3, a4, is a2, a3, a4, etc. x2 is a3, a4, a5, etc. Okay, so basically the digits keep hopping down your number. Fine, but what does that mean? I start with a x naught, then it has some precision, and then the digits which are far right, at the end of the line, okay, way at the end, you don't even bother, because at that position, it's fine. We have to give up precision at some point, and in the beginning it makes the slightest difference to everything, right? So suppose this was 2 to the power 10 or something, so 10th decimal place, it's just fine, you don't know it too well. But in 10 steps, that decimal, that digit has come to the leading place. So it has gained extreme significance. So basically, for instance, a small change in the initial condition, say A10 was 0, but it should have been 1. Okay. So it's very tiny. It's 2 to the power minus 10 difference in the beginning. Very respectable precision. But by 9 iterates, it makes a huge change in xn. So that is how fast it is making a difference. So it is not like small changes make small differences at the end, but small changes make huge differences in a very short time. Okay, so this map is one of those cute maps which show things very straightforwardly. I wanted to flag one more thing. So there is this extreme sensitivity. Everything looked very complicated in that figure which I showed you. However, inside this, there are also periodic orbits. And I will tell you that these exist, but they are all unstable. So first, let's see, can we find a periodic point in this? Okay, we have found that things are a Bernoulli shift, which is very sensitive, but can we find a periodic point? So what is a periodic point? Definition: if the orbit successively cycles through p distinct points, so x0, x1, x2, all the way xp minus 1, comes back to, so xp goes back to x0, okay, so p points, and it keeps cycling through them, then you say it's a periodic orbit of p iterates. So for instance, if I have x0 written in binary in this fashion, 2/3 written in binary is 0.101010 forever and ever. What is the binary expansion of 1/3? It's 0.010101 forever. Now, under the shift map, 2x mod 1 map, this is just, the dynamics is just a Bernoulli shift. It just goes down. The decimal point just hops down the x0. So x1, it hopped down, then it became 0.10101. So it became 1/3. Next point, it went one more, it became 1.010 2/3. So you got a 2 cycle, a cycle which repeated every 2 steps, 2/3, 1/3, 2/3, 1/3, etc. So in general, then a period P will come from an initial condition which has P of these, a string of P numbers repeated in segments. So you have some pattern of a string of P numbers, then you repeat that forever. Okay. So why? Because then, of course, if you keep hopping down P times, it come back to the exact same thing. Okay. So I can now ask, how many different initial conditions are there that return to themselves after P iterations? Since all you need is a sequence like this, which repeats after P iterations, I just need to know how many distinct sequences like this are possible. Remember, each of the A's are 0, 1. Okay, there are 2 values possible. So there are 2 to the power P distinct sequences. So the number of distinct periodic points is 2 to the power P minus 2. I've put minus 2 because 2 of them are the fixed points, which are at the end. 0, 0 goes to 1, 1 goes to 0. Those are fixed. And there are P points in each cycle. So I divide it out by P. and I have a number like this. Now let us put in a few numbers into this formula, and you find, say, if P is 11, so a periodic orbit with 11 distinct points, so the 12th one goes to the first one, etc. Then the number of distinct orbits that you get is 186. So that many periodic points are there in the system. But you go up a little, say 17, it's 7,710. So basically, it's just galloping. It's like an extreme proliferation of periodic points. Okay. So not only is there chaos, but there are also an extremely large number of periodic points. And in fact, you can do the same calculation if P is not prime. That one was for prime. If it has some integer factors, and you can write it in this fashion, then of course, some of the points will lie on the lower period. So for instance, if it's 2, then of course, a period 2 will also be a period 4, because anything which repeats 2 times also repeats 4 times. Okay. It'll also be a period 6, because everything which repeats 2 times, repeats 4 times, repeats 6 times. So you have to make your calculation is a bit harder. However, when P is large, it still has this order of magnitude, okay? 2 to the power P by P. So extremely large. So what we have is, did anyone ask a question? I keep hearing, no. Okay. Yes.
Ma'am, somebody has raised a hand.
Oh, I'm not seeing that. I'm sorry. You could just unmute and ask, because
Conan, please go ahead.
Because somehow I don't see the what do you call it? I can't see my screen. I don't know where yes, but please unmute and ask. Yes, please ask. Yeah, sure.
Yeah. Is this like, is this a if and only if condition, like even if you like go to say like higher dimensions, is this the presence of periodic orbits of all periods does it always go hand in hand with chaos? Or?
So all systems is not so I won't go so far. It's not provable for everything. However, for classes of higher dimensional systems, it is indeed true. So you have to be a little bit careful on what class you identify, but it is true for most generic classes of higher dimensional systems as well. Okay. So we have to be a little bit careful, because here, of course, so I'll just probably at the end mention a theorem by Sarkovsky, just a statement which will tell you what sort of classes of systems would give it. And the thing about high dimensional system is that some of them reduce in some fashion to these maps, and then of course you have the same set of results for them. Okay, but
Ma'am, Sharkovsky's theorem is just for one dimension.
That is one dimensional map, but a lot of them would reduce to. So, for instance, okay. So, as I said, once if I take question, might go a bit far afield, but say the Lorentz system, which is actually ordinary differential equations, 3 ordinary differential equations. So it gives chaos for certain parameter values. It is but in these chaotic, and these are orbits which are continuous time, you can define a map in these systems by, in a certain way, by taking maxima of a certain one variable, etc., which is effectively a 1D map. And then once that is true, you can take the results. It is a unimodal 1D map, and you can take a lot of the results from 1D map onto it. So there has to be a certain reduction to these. So sometimes you may not be able to find that exactly, or you may not be able to find that rigorously. But in a large number of cases, you can say that. For 2D cases, it's much easier, and higher dimensional maps, it's much easier. For flows, you have to make a map out of the flow, either through Poincare sections or by stroboscopic methods. And if you can do it, you're good to go. Okay. And the short answer is that you can for many systems. Yeah. Okay.
Sorry, just one small thing. Could you mention like some keywords or some names of those generic systems which you told, which go in which
Yeah. So, for
Although,
instance, in the Lorentz case also, so actually, I'm not talking about flows. So, so maybe I'll tell you at the end then, because
okay,
it will
yeah,
take
yeah,
me into flows, which is a completely different story, or to higher dimensions, which again. So I'll get back to you. Okay. So let
okay,
me
yeah,
sort of, yeah, because yeah, to tell you all a little bit, and so keep it in your head. I will sort of give you a little bit more on that. Yeah. So,
Excuse me, ma'am.
right, yeah, yeah, yes,
Sometime before, a person had asked in the chat box a question. Could I read it
oh,
out?
yeah, sure, sure. Let me see. Maybe I can see it. Hang in there. I should be able to see this. Yeah, yeah, yeah. Okay, 1 minute. How do I see chat? Uh, Okay, I don't seem to man. Yeah, yeah, I can see it. Right. So although Poincare bend is a force is bounded in 2D to have a limit point, but 1D to, yeah, right. Yeah. So do remember that first, of course, that those are so in fact, that is Poincare-Benedictson is what gives you that necessary condition of 3 for ordinary differential equations. And the other thing is that invertible map, you will need so there actually basically from a section you can get so you would need an invertible map in order to get this continuous orbit. So for that you'll need 2. And so this is not, so you can't so you can't map that flow into a 1D non-invertible map. So which is why but this is in a special class. Yeah, yeah. So so from right. So basically, since you know Poincare bend, I don't know how many of you all know it. That's my problem. So I did not go into flows because of that. But essentially, that the result which I had given, where n has to be greater than equal to 3, that bound comes from the fact that if you are in 2D, you can only be a limit cycle or a fixed point. You can't. There is no other possibility due to Poincare-Benedictson theorem. So you have to go to 3D. Now, if you go for a continuous orbit in 3D and you want to get a map out of it, it's going to be a invertible map, because you have which is unique, and that is how you get a 2D map out of the 3D flow, which would give that to you. But for non-invertible, that restriction is not there. Okay. So right. So I'll continue a bit. So now the question is that you have all these solutions. Okay, you have a proliferation of solutions, but you don't see them. So if I ran my program, if I went and did an experiment, I will not see these periodic points. So what is the deal? So the thing is, in order to actually see the point, I mean, see as in either it comes out in your numerics, or it comes out in something which is, in your experimental box, differences change to write an equation for the differences now, right? And if you use Taylor series expansion, you can express it in terms of sometimes we call it a stability coefficient. I've put a subscript p here, which is denoting the pth orbit, and this is just a product of the df dx evaluated at the different points in your orbit. Okay, so so since of course this is I mean, you can start anywhere in the orbit, and of course, it's just a product, so it wouldn't matter where you start. So that part is not important. But what is important is that you have to evaluate df dx at each point in the orbit. Okay, that is what you have to do. That's your task. And this is a summary. If the deviation from the periodic orbit grows, that is, your lambda is greater than 1, then you have an unstable situation because your deviation is growing at each stage here. Okay, so if you write it out, there's going to be an exponential change. And if it is less than 1, then it reduces by a factor each time. Okay, so this is the stable situation. And there is also one which you should keep in mind, which is called super stable, where it's exactly 0. It's a very, very special point, which is, of course, stable. Obviously, it's less than 1, but it is also extra special because it's exactly 0. Okay, so this is the stability coefficient. Now, what is it for the tent map or the 2x mod 1 map? All of these. Now, all of them are unstable. And I can do this in like two lines because it is so simple, because f prime is always 2, the magnitude. So for the tent map, it may be 2, it might be -2, depending on where your periodic point is. For the 2x mod 1 map, it's always 2. And so it is just 2 to the power p, which is always greater than 1. Okay, so every single one of those periodic points was unstable, which is why, though there's such a large number of them, you never see any of them, okay, in your numerics. So you have a dense set of unstable periodic points, that is, given x and epsilon, however small, around any point x, there is at least one periodic point in the interval given by this, okay? And one point of period p is there in this particular interval, which you could also see from the graphics. And of course, you can choose your p in such a way that you have at least one point of period p around an interval of arbitrarily small size. Now, the periodic points are countably infinite. And they are a set of measure 0. This implies that if one chooses an initial condition x naught at random from the interval, the probability of x naught being a periodic point is 0. So chaotic orbits are typical. Okay, so this is the part I wanted to bring to you. Two things which were a little bit contradictory. One was it's very simple, but you got something very complicated. Second thing was that that you not only have this, you have a skeleton of these unstable periodic points sitting inside the space where the typical orbit is actually chaotic. I just thought I'll put 2 slides to define the Lyapunov exponent, because I can't leave you all without defining it once. It is actually very, very related to your lambda stability coefficient, which I gave before. But and in literature, unfortunately, both are called lambda. So this, though, is the exponent to which the exponential has to be raised in order to get the separation after n iterates. And a positive Lyapunov exponent is the gold standard for signature of chaos. The more precise and actually more computationally useful formula is to take logs and the limit properly, and you get an expression like so. Now, the part which if you wanted to write a program to do it, if you were clever, you would never implement a program with this. Rather, you would implement this in your program. That is to say, you write it as a sum of the logs, because otherwise your errors get out of hand. So this is taken as the computationally useful formula for lambda. Okay, and of course, you start with some x naught. It's supposed to depend on x naught, obviously. Of course, your trajectory is infinitely long, as much as your system allows, your computer allows you, if you're doing it computationally. Otherwise, of course, in principle, n tends to infinity. However, though it's supposed to depend on x naught, if the x naught is in the basin of attraction of a given attractor, which means it's a set of initial states which are going to the same type of dynamical object, then no matter what you do, you get the same answer. So for fixed points and cycles, it is negative. And for chaotic attractors, it is a positive number. Okay, so this is something which people routinely compute in order to say that something is chaotic or not. Okay, and for the tent map again, it is just log 2, because of course f prime is 2, and so log, and it's the same at every point, so it's log 2, it's always chaotic. Okay, a very simple one-line calculation. Okay, last 15 minutes, I thought I should mention the logistic map, because I have not used the word bifurcation, which I promised. Maybe 20 minutes I'll take at most. Yeah, maybe 20 minutes to tell you a little bit about the whole thing about qualitative change of solutions, because that is not easily demonstrative in the maps which I showed you before, but comes out beautifully in this particular map.
Excuse
So
me,
if
ma'am.
yes,
There is a doubt in the chat. Should I read it out?
sorry. I have to keep going back and forth into my, yeah, okay, yeah, you read it out. Yeah, that might be
Uh,
easier.
Manraj Guman is asking, can you please explain what is the delta in your notation?
Delta, okay. Delta was just the difference between, so you start off two orbits. One starts at x naught and the other starts at x naught plus delta naught. So delta naught, so the subscript is the deviation at the time iterate. So at n equal to 0, when you start off, it is delta naught. Delta n is the deviation at the nth iterate. So what you want is an expression for the deviation as it goes in time. So if the deviation grows larger by a factor, you know that it's going further and further away from the solution. You started off, whereas if it is contracting, you will get a stable point. Okay, so that is why you're tracking the deviation. Delta is the deviation of these two orbits, one starting at x naught and the other starting at x naught plus delta naught at time. And then, of course, it goes to this one goes to x1, that one goes to x1 plus delta 1. So it keeps, the deviation keeps changing with n. The whole point is it growing or is it contracting or shrinking? Okay.
Sorry, can I ask something related to this?
Yes, huh?
So here, the way you have defined Lyapunov exponent, it depends on the point, right? Xi, it depends on which point you're taking it for.
X naught, yeah. It depends on x naught. But it starts at x naught, and then, of course, you're taking an extremely long orbit, right? That's the whole point. So n tends to infinity after, it starts at x naught, and then, you track these two neighboring orbits for a long time. So, of course, in the definition, it depends on x naught. The strict definition depends on x naught, as is put here. However, if the x naught is this, so there is this phenomena which I will show you in 2 minutes, called transient. So what happens is sometimes it sits on the attractor, because the whole interval is your attractor. However, there are cases where it might take a few iterates to get to the attractor. But the point is, if you take an infinitely long, technically, orbit, then it spends enormous amount of most of its time on the attracting points. So if the x naught is in the basin of attraction, that is the initial condition which leads to that attractor, then this answer will come out to be the same. But of course, technically, so in fact, in higher dimensional systems, this is indeed a point. You can map out your phase space, saying that, lambda is this in this part, lambda is this in that part. It will depend. And in fact, it does depend. Okay. But in the basin of attraction of a given attractor, it's the same number. That is the point. I'll show you a picture shortly in this one to give you a sense of the thing. Oh, but I'm pretty short of time. Okay, let me just show it to you. So this is one of those things which people in biology are forever doing, and probably Sutit has shown you many times. Okay, now this is a parabola. Okay, the other one was had a tent, was two pieces, two straight lines. But here this is a parabola whose height changes with r. That's it. And now you can also see where it's going to remain bounded. It's going to be remain bounded because at its maxima is at half, if of this function, and the height of the maxima is r by 4. So of course, if r is more than 4, it's going to stick out of the box. So it's going to then bound off to minus infinity. So, but if you remain if r is less than equal to 4, and if you start with any iterate inside the interval, you will remain bounded in the interval. So this is your interval, which gives you bounded orbits. Now, if I look at fixed points here, I just have to solve the simple equation, xn plus 1, which is a function of xn, should be xn. Okay, that's how I will repeat every step. Okay, and so I just have to solve this, and there are two. Now this is a quadratic, so I have these two solutions. One is 0, always solves it, irrespective of r, and the other one is 1 minus r. This depends, the solution depends on r, the exact number. Okay, now to look at the stability, I again have to do df dx evaluated at these points. So of course, I just have to evaluate this object at different x stars. So for instance, if x star was 0, I plug it in here, and this one goes to 0, so I just have r. So if r is less than 1, absolute value of f prime is less than 1, and it is stable. So if I start my computer program, doesn't matter where I start, it is going to go and stick to this part forever. So this is what I wanted to show you when I said transients. So depending on where you start, the first bit is not generic. It depends on where you start, your x naught. So if I started here, it would have a different trajectory. However, after this part, which we call transients, that is, it will pass, it will go away, what we are left with is the attractor. So these are the attracting points. And all these points, wherever I start, if it comes and hits this point, then it lies in the basin of attraction of this point. Okay, and here, anything in the interval 0 to 1, doesn't matter where I start, if I leave let it settle in, give it a bit of time, it will go and sit at this point. Okay, and this is of course going, so if I compute something for ever and ever, this is the dominant part. And now for 1 minus 1 by r. Here, if I plug it in, I get this particular inequality for stability. And so if I open this out, it tells me r between 1 and 3 will give me the stable point for 1 by r. And this is super stable at one point, because at r equal to 2, 2 minus 2 is 0, so f prime is 0, and I had told you that this was the super stable point. So basically, it is from 1 to 3, and there is this sweet spot in the middle at 2, where it is the most stable. So it just gains stability, becomes super stable, and then goes out and loses stability at 3 again. Okay. So this is what would happen between 1 and 3. For instance, here, if I plug in the value of 1 minus 1 by r for r equal to 2.5, I get 3/5. And indeed, if I start my program, I will get stuck nicely at 3/5 forever and ever. Okay. Now, graphical solutions are very important in this business, because here, of course, you can do it, just one line of algebra, but it can get hairier for other things. So basically, a graphical solution is that you look at the diagonal, the 45-degree line in the box 0 to 1, 0 to 1. This is your mapping box. And the intersections of this with the curve is your fixed point solution. These are your fixed point solutions. Okay. So you can see how first you had one, and then you start generating the second one in the positive quadrant. This is your super stable one. Why? Because the stability of the points is the slope at the intersection, f prime. So f prime, you can, to the eye, you can see is this horizontal thing here. That's your slope, that's your tangent. So this is the super stable point. Indeed, this is 2. And then you go here. And as you can see, this one, clearly, this is more than steeper than for a 45-degree line, minus 45-degree line. And so this is not a stable point, but it exists. Okay, it exists. And so greater than 3, what happens is you lose stability for period 1 and go to period 2. And period 2 also loses it and goes to period 4. Okay. And so what you get is a sequence, an infinite cascade of bifurcations. What we call bifurcations is qualitative changes in your solution as you sweep through a parameter. And this is in a nutshell what would happen here. And I'll show you a close-up of it, and then I'll tell you what happens at each little point in 10 minutes or so. So if I look at it closer and closer, I find more and more detail. So one thing to the eye, you can see, this is period 1, went into period 2, went into period 4. So there is a doubling of periods. Then it seems to accumulate and stop somewhere. After that, there are these chaotic bands. And inside the bands, there are white looking things which are windows. These windows are windows of odd cycles. So here there's period 3, 1, 2, 3. Here there was actually period 5, you can see it better here, 1, 2, 3, 4, 5. So you can keep zooming into this bifurcation diagram, and it blows your mind, because inside this little bit here, you contain this entire sort of sequence sitting in. So this is a blow up of this tiny region here. But if I zoomed in even further, I will see a copy of that full bifurcation diagram in there. Okay? So it's very, very complex. And there are 3 types of bifurcations that gives rise to this complexity. That's the nice part. It's very complex, but exactly 3 things happen. One is called transcritical, where there are 2 solutions which just exchange stability. So you have a stable solution in this which becomes unstable, and the unstable one picks it up from the stable one. So they essentially swap, and so no new solutions are created, no solutions are destroyed, but the stability is just changes hands. And so in the logistic map, where did that happen? It happened at r equal to 1. So this was x equal to 0. Remember, x equal to 0 is actually extinction, because your entire logistic thing, your x sits at 0, which means x being your population is always 0. So this solution is stable up to r equal to 1, as we saw through the analysis, through the algebra, and then gives it up. But it's always a solution, except it is unstable. Same thing happens to to this solution, 1 minus 1 by r. It exchanges stability here at r equal to 1, as we saw in the algebra, and gains stability here, and will lose it through a different mechanism on the other end. But this part is the transcritical point. The second bifurcation is pitchfork. Here, 2 things happen. One is 2 new solutions are created. So where there was 1 solution before the bifurcation point, there are now 3 solutions. One is a continuation kind of the old one, but 2 new things have come out of the blue. So 2 solutions are created. Solutions are created now. And additionally, stability is exchanged. So the existing solution loses stability, and the new solutions are stable. And where do you see that in the bifurcation diagram? So this part was the transcritical one. It went, you see the pitchfork at this point, where you period doubled. So the unstable part, remember, in a numerical bifurcation diagram, all the unstable points are invisible, because no matter where you start, you will never see them. Okay, so I am drawing it with dashed lines to remind you that the solution exists but is unstable. Okay, so this part you won't see, but these 2 new stable solutions are the ones you see. So all the period doubling that you saw, so this was transcritical, this is pitchfork, and so invisible is that unstable 1 minus 1 by r solution, which goes all the way to the end. Here actually is the same mechanism locally, where again there is an unstable period 2, and which gives way to these 2 new solutions. Okay, these are all created through pitchforks or period doubling. If you look at it graphically, this is what it looks like. So r equal to 2, I am plotting now f of x composed twice. So x n plus 2 versus xn. So start at xn, what is the second iterate? When r is 2, so 2x 1 minus x, very shallow parabola. This green one is the first iterate, purple magenta one is the second iterate. As you can see, it cuts in the exact same two place. Why? Because if you are a period 1 solution, you are also a period 2 solution. Okay, so these are the two common solutions. They're trivial solutions because they're also period 1 solution. However, as r changes value, the shape of your parabola, of course, it gets steeper, and your second iterate, this is f2, gains this shape such that it intersects it in two additional places. So this one is the common intersection with the fixed point. So two fixed points are there, but there are two additional fixed points, which is these two values. Okay, that's how the locally at every point, that is what is happening to your map. Two new intersections come. And indeed, the whole sequence you can get is where one orbit loses stability and a new one, a doubled orbit, gains stability at that exact same point. And that whole sequence has been done with extreme numerical accuracy by many people. In the early 70s, it was a big thing. Of course, now it's somewhat routine. I should also mention that there is a sequence here which tells you how these numbers shrink, and it actually appears to be common to a large class of maps, namely unimodal maps with a quadratic maxima. All of them have this exact quantitative factor of 4.669, by which this ratio shrinks. So what does it mean? It means that, say, period 1 had a range compared to period 2, compared to period 4, and you look at the ratios at which the ranges are shrinking. Of course, it has to shrink. It accumulates, right? It squishes and comes to a different point. And this accumulating point you can get from this geometric sequence very easily to be 3.57 something. Okay, so this is also a factor which comes in the period doubling cascade. So last 2 minutes, okay, literally, what happens between that 3.57 and 4? There's quite a bit of space, and you could see lots happened. But one of the things you noticed, so all this stuff was happening, all of this happening after 3.57 and 4, all this thing. Okay, but let's look at these periodic windows which came. What created those? It can't be period doubling because they are odd. Okay, you can't create an odd cycle through that. Okay, those solutions did not exist, so it can't be transcritical. What gives rise to those orbits is something called a tangent bifurcation or a saddle node. And this is the schematic of it. Before the bifurcation point, there were no solutions. Right after the point, out of the blue, springs two new solutions. And they are of the kind, one is stable and one is unstable. What is nice is that these three types of bifurcations are generic, and they are the kinds which underlie even high dimensional objects. Okay, so this is even flows. So if you did ordinary differential equations, the classes of bifurcations you get essentially these three, which are generic, which means that you add some small terms to your function. If it's structurally stable, it'll give you just these three types. That is enough to generate all these qualitatively different types of solutions. So here we are not doing this, what is the solution? We are asking, is the qualitative nature of the solution changing? When is it changing and how is it changing? Okay, so this one, birth of period 3, is through a tangent. If you look at this is xn plus 3 versus xn, so third iterate. Okay, I showed you the second iterate here. Now this is the third iterate. And this is what it looks like just close to the three cycle window. Just before it, only two solutions are the period 1 solutions. As I said, period 1 solution is also period 2, is also period 3. So indeed, those two intersections are there, but no other. The red curve is missing skimming the diagonal. But here, the curve, just when it enters the window, cuts it in a way that it generates 6 new intersections, 3 of which are stable and 3 of which are unstable. So that is how, through this kind of a bifurcation, you get this 3 cycle in this map. So this is a summary sheet. I've taken a little bit more time. Oh, maybe not. I've just about finished an hour. So this is a summary sheet of the kind of bifurcations that you got in order to produce that very complicated diagram, this one, which is fun to do, this one and this one, etc. So all of these are captured by this summary sheet. And, so there is a kind of very, there's a structure to it, which is not a zoo. So it's not like, anything, any old thing can happen. It's not like that. It's a set of things which can happen, which is that you could either have a stability exchange, where one solution is always a solution independent of R, the other solution depends on R, the shape of the solution, and you exchange it exactly at a point where they coincide. After that, you change stability. That's transcritical. Pitchfork, which gives rise to all the orbits with periodicity 2 to the power m, and which looks like so. So this is how doubled period orbits are formed, and that accounts for all the bifurcation from 1 all the way to 3.57, the accumulation point of that period doubling cascade. And the last one I said was the tangent one, which gave rise to odd cycles. Okay. So I had one slide. I don't know if I should show it or not. Before this was my summary, but I had this one slide. I thought I'll just keep it there. So this was the theorem which I was mentioning. The reason I thought I'll put it there is that period 3 implies chaos was historically actually the first technical paper where the word chaos was used technically. I mean, it's a word in English language, so people use it, to describe anything from traffic to politics to what have you. But the technical word, something which is used in common usage makes its way into technical literature, is sociology also. But the first time it came was Lee and York's paper in American Mathematical Monthly, I think, in 70 something, 5 or something. And they used this particular word. And basically, this is a statement on the existence, but not on stability. So if you order positive integers in this fashion, so odds first except 1, 2 times the odds, 2 times 2 times the odds, 2 times 2 raised to the power, m, etc., all the way, times odds. Then you start listing powers of 2 in decreasing order all the way to 1, which you can take as 2 to the power 0. Okay. If you look at this sequence out here, the theorem says if period P occurs before period L in this list, then the map also has the periodic orbit of period L. So if you see 3, you can be assured that all these solutions exist. So of course you see P, you see 3 because that is the one that's stable. All the others are there. They are like ghosts. So the ghosts of every unstable period is sitting there, okay? Because remember, in all these things, the unstable guy perpetuates. So this stays, okay? So is there. This one becomes unstable, but it stays, okay? And so in some sense, that is, is something which you know. And it also, what is interesting sociologically is that when this theorem came about, nobody had done any numerical simulations. Nobody had done any sort of, there was no feeling for what these maps look like. There was, like in most of us, run to the computer and just, produce all these, we get a sense of what it is doing before we even try to account for it. So we have intuition from like a numerical experiment, whereas they didn't have that. So in a sense, that is the interesting thing. It's not terribly difficult to prove, but it is still of great consequence, and also interesting that it came well before all the other ways of understanding the system. Okay, so I'm crossed my hour mark. So let me just put this as a summary slide. So what I thought I'd tell you is how the simplest of iterated maps, first just piecewise linear, the tent map, 2x mod 1 map, and then a map with the simplest of nonlinearities, namely a quadratic nonlinearity, the logistic map. How such a simple set of maps gives rise to so much complex dynamics. Okay, so not only did they give chaos off the bat for 2x mod 1 and the tent map, provably so, both for sensitivity of initial conditions and and if you compute the Lyapunov exponent also from that, which could be done there exactly. In the logistic map, you also additionally got this whole spectrum of bifurcations, which gave periodic orbits of all orders. So you got everything that you need to get out of the system, from a fixed point to a cycle which went over 2 values, to 4 values, to every possible scenario that you can have, onto full-blown chaos. Okay, so and these came through 3 different types of bifurcation. So here the whole thing is qualitative changes in dynamics is what you're after, and they were these 3 classes, which are actually pretty generic and are there also for differential equations. Okay, so it's not that it's so special to the map that you will never see it again. It is actually pretty common to a whole range of things. Okay, so I'll stop here and let me see if I can. Yeah, right. Yeah, so I'm done. Over to you all. Should I stop sharing? Maybe I'll stop sharing.
I have some questions.
Yes, please. Yeah.
Okay, sorry, go ahead.
No, okay, you can go ahead. I'll ask later.
Yeah, so in one slide, ma'am, you had shown that the set of periodic points is countably infinite. Were you just referring to that specific map, or were you talking about some generic class of?
It's of course I had shown it for that specific map because if you see, I mean, the whole class of initial conditions which can give rise to periodic points was when the sequence of p a string of p repeats, right? So it is now this you can show, I'm sure, pretty quickly that this is going to be a countably infinite set. Okay, and for this one, now a very large number of maps actually fall under the class. So this was for 2x mod 1 because there you could show it very easily because you just had to show that the strings had to repeat. But the tent map is also conjugate or maybe semi-conjugate to the 2x mod 1 map. The logistic map at r equal to 4, there's a transformation with sine square pi x, which actually transforms it to the tent map. So it also is in the same class. So in fact, so because you can make that transformation for even the logistic map at r equal to 4, you can deduce that at r equal to 4, where there's this full chaos over the entire interval, this dense set of unstable periodic points also exist. This, of course, through the bifurcation sequence in a different way, but you also know because you can show through this transformation that it is topologically equivalent to a tent map. Okay, so various things. So these are exactly shown in high dimensional systems. For some things you can exactly show that there is you can transform it to effective map where you can show this. It is not always obviously possible in an exact fashion to show it because some of the sequences are complicated. But as I was telling you, even in flows, there are the same sequences are there in terms of change in qualitative nature of solutions. So those old solutions persist in unstable form over a large parameter range. And if you can show that it exists and is unstable, often it's possible to show that you have those solutions, but it's not as easy as in this one. So that's why I chose this example, because it's easy to do in 10-15 minutes. Yeah.
So in general, like what you implied is that you will have these countably infinite sets of periodic points even in like higher.
In many cases, yeah. So there I can't say that every case will. So there I can say that there are many examples of those where it does happen. Cat map I showed you would have it, for instance, but not. So obviously you have to be careful. You have to see whether there's. It's whether the map is too limited or not. So for instance, very, very simply, even in the context of this, if I took my logistic map at, say, r equal to 2, then where is infinite? There are only 2 solutions, and I mean, you can count them, or r equal to 1, I mean, or less than 1. So even with the same functional form, with the change of the parameter, you actually didn't get, so how careful you have to be, right? I mean, so for instance, so what I was saying is that suppose I took my logistic map, right? So at r equal to 2, I have only 2 solutions. I mean, certainly not the infinite number or anything. Exactly 2. And here I get, okay, 4. But the point is that you can't, so it's the same functional form. It's the same old form. Same old form. It's just that the parameter r, as you changed it, your number of solutions changed, and of course the stability of solutions change. Only at r equal to 4, when it touches the top here, is it the same essentially as the tent map, but not here. So sometimes just looking at the similar functional form, you might run and say, maybe I'll get everything. So you have to be careful, obviously. Even for this, but there is very large number of examples where that indeed holds. Yeah.
Ma'am, and so regarding bifurcations, is there some sort of like some at least naively it seems like there might be some sort of algebra of these fixed points where if you count some as stable as +1 and unstable as -1, there is some type of conservation, but is that
not really, but actually it is it's for maps. I find it easier to motivate it graphically, but for differential equations, actually it's easier to do. There are these normal forms. So locally, remember, it doesn't have to be in it, just at the bifurcation near the point where your stability is changing. Locally, the form of your flow of the function which is giving you a dynamical evolution has to have a certain form. So there are these normal forms, which we call normal forms, where so basically you can change the variables in such a way so that it looks locally that form. So each of these have different types of forms. There may be r minus r x square, r x1 as. So there are different types of normal forms for each of the 3 types of bifurcations. So that is actually, once you see that form, you know that what I showed you graphically, that little picture is what is going to come locally at that point for your system. Now, so that I think is the best way of understanding it, and not through through counting stable, unstable. That probably is not very good. there are ways in which to understand different types of fixed points, or things which are attracting or with different through the index theorem, but that is I have to go to 2D for that. And there also it's not the stability, but it's the nature of the flow. So stability is not captured by that. Yeah, but it's very easily captured by the normal forms. Yeah.
Excuse me, ma'am.
But remember, it's local. It's very local. So it's what happens. So which is why that scaling relation holds for any unimodal map with quadratic maxima, because you just have to locally, if you do the right transformation, each part of the pitchfork looks like itself. Even sitting inside the 3 window, the pitchfork bifurcation that was happening locally was looking like what it looked like right at the outset. Okay, so that part is once you get that idea, then the rest you have to, of course, hard work, but